Hello everyone. My name is Siddharth Tanwar. I am currently pursuing my master's in technology from National Institute of Technology, Karnataka, Surathkal, and my specialization is in signal processing and machine learning. So, today I'll be teaching you about trees data structure that would be very helpful in your data structures and algorithm journey, which will in turn help you in your semester exams or in your job interviews, etc. etc. So let's start with the lecture. So, introduction, a tree, imagine a tree and make it upside down. By upside down, I mean the root is in the tops and the leaves are in the bottom. So, a tree data structure is similar to that only. So, a tree data structure is an hierarchical, non-linear data structure of nodes connected by edges, where each node stores data and the structure forms from a parent-child relationship. By hierarchical, we mean in level by level. By level, I mean we would first go to the topmost, then after hit the second top, and then so on. And for an example, we can take the hierarchy of the school. The first is the hierarchy of a college, let's say. The first is the dean, then the first is the principal, then the dean academics, then the dean planning, then the teachers, then the professor, etc. etc. That is the hierarchy. So, similarly, in this way, the tree is also in hierarchical form. First, we will go to the first node. Then we can go to the nodes connected to it, and after that, we can go to the nodes connected to the nodes downer to them. So we are going in an hierarchy, first starting with A, then B and C, then D and E, then F, G, H. F, G, H. And by parent-child relationship, we mean of the node from which the other nodes are connected. Here, let's say the node is A. From A, B and C are connected. So A is the parent, B and C are the children. So making this a parent-child relationship. The tree is also called an acyclic graph as it contains no cycle. So by graph, what we mean? A graph can be cyclic. A graph is also a tree, but it is cyclic. So let's make a graph. For example, a 4-node graph we are making, which contains cycle. And let's make this graph directed graph. A, B, C, D. This graph contains 2 cycles. First cycle we can take as A, D, C. C, from A it goes to D, then D to C, then C to A. And second cycle we can take as A, D, C, D. As it goes from A to D, D to C, C to B, B to A. It contains a cycle. So a cyclic graph cannot be called as a tree. A tree is a graph as it contains nodes and edges, but it doesn't contain a cycle. That is why we call it as an acyclic graph. A tree, let's come to the number of nodes and number of edges relationship. Always a tree would have n nodes. Like, let's say here in the example I have given, the number of n is 1, 2, 3, 4, 5, 6, 7, 8. N is 8. So as we do not contain any number of cycles, so the edges that connects 2 nodes would always be 1 less than that of the number of nodes. So edges is n minus 1. So here we have 8 nodes minus 1, which give us 7 edges. Let's count it. 1, 2, 3, 4, 5, 6, 7. So we are right. Coming to the next slide, we have the structure of the tree. as I said, the tree is in a hierarchical format, so we take each level or height in hierarchy format also. So the first level, which has the root is the first node from which the tree starts. So the first level is always at height 0. Second level is at height 1. Third level is at height 2, and fourth level is at height 3. So if we know the level, we can take out the height by height by this formula: height equals to level minus 1. So got to know how to name the level or the height of a tree, and the first node from which the tree starts is called the root. The first node from which the tree starts, it's called the root. So, and we can also call it the parent node. What we can call it? Parent node, as from the root or the parent node other nodes gets connected. Therefore, similar to a tree, inside a tree we also have subtrees. Subtrees, as in, say, the triangle which is made of B, E and F, we can call it as a subtree, as in itself it makes a tree structure, saying that B is the parent, E and F is the children. So nodes lying on the same level, nodes lying on the same level can be called called siblings. Can be not, can is wrong, is called siblings. So we can say that B, C, D are siblings, E, F, G, H, I are siblings, J and K are siblings. Moving on to the next slide. So let's come to the types of trees. We have 11 types of trees we will be talking about here. The first is rooted tree. A rooted tree is a tree that I showed you earlier, and it has a similar, the structure is the same as I taught you. So let's come to a general tree. And the definition of the general tree is, when each node of a tree is having 0 or more children, then it is called a general tree. See, in diagram B, each node has 1, 2 or 0 children. For 0 children we have a F node, for 1 children we have B node, for 2 children we have a R node, and for 3 children we have A node. Okay, so it is a general tree. It has no rule of how many nodes or can a parent have. So let's come to the forest. A forest is a collection of trees, collection of 2 or more general trees. 2 or more general trees is the keyword for this. From a single tree we cannot make a forest. For making a forest we need at least two trees, and it might be general, it might be any kind of tree which we will be studying ahead. K-array tree. A K-array tree is a tree in which each nodes have either 0 or K. Either 0 or K. By either 0 or K we mean let K be 3. So each node can only have 0 or 3 children. For example, A node has 3 children, D, E and F, and root node have 3 children, A, B, C. Moving ahead, here comes a binary tree. A binary tree is a tree in which each nodes are having either 0, 1 or 2 children. Unlike K-array tree, the binary tree is a general tree which we gave a name, as it can have maximum of 2 children. For example, in diagram A we have a binary tree, and see, each level has either 2, each node has either 2 or 0 or 1 children. It is different from a k-array tree. Full binary tree. A binary tree where each nodes either have 0 or 2 children. We can say a full binary tree as a 2-array tree. As by definition, k-array tree has 0 or k children. So here 2-array tree has 0 or 2 children. In diagram B, node 20 has 2 children 10 and 15. Node 15 has 2 children 30 and 26. And node 30, 26 and 10 has 0 children. So it suits the it fulfills the definition of a full binary tree. Binary search tree. A binary search tree is a tree in which the value on the left subtree is lesser than the parent or the root, and the value in the right subtree is always greater than the parent or the root. Moving on to the next slide. Type of trees continued. We have got Abel tree. A binary search tree is an Abel tree. For an Abel tree, to call a tree an Abel tree, it first needs to be a binary tree. Is tree if the difference between the height of the left and the right subtree is either 1, 0 or 1, minus 1, 0 or 1. So let's go to the example A. We have how many levels? Level 1, level 2, level 3 and level 4. So and if talking about the right, we have 4 levels, and talking about the left subtree, we have 3 levels. So let's count. Taking right, we have 4 levels, and taking taking right subtree, we have 4 levels. Taking left subtree, we have 3 levels, and 4 minus 3 is 1. So it comes out as a balanced tree, as the difference between the height of the left and the right subtree is in the range of 1, 0 or minus 1. Going to the next tree called the complete binary tree. A binary tree is a complete binary tree if every level is full except possibly the last. By except possibly the last, we mean that in the last level, the upper node can have either 0, 1 or 2 children, not more than 2. For example, in B, the node 1 has 2 children 2 and 3, fulfilling the definition. Node 2 has 4 and 5, fulfilling the definition, and node 3 has only one node, which is 6, fulfilling the definition. As in the last level, node 3 is not fulfilled, which satisfies the definition. Heap. A heap is also a complete binary tree in which either the parent node is the largest, or a complete binary tree in which the parent node is the smallest. True for a full tree and also the subtree. For example, for a max heap, we have diagram C.1 in which 90, which is the largest number, is on the top or the root. 70, which is the third largest, is in top. 89 is also in top. So making the definition of max heap full true. And for mean heap, we have 1 in the top, fulfilling the definition of mean heap. 3 in the top, fulfilling the definition of mean heap. So let's move on to the next. Let's come here to tree traversal. By tree traversal, we mean going to each node and printing the value in that node, thereby printing out the complete tree. So let's first come to an in-order traversal. In-order traversal is a depth first search. By depth first search, we mean we go from top to down. Depth first search. First we will go in the depth, then come up. Depth first search method for visiting nodes in a binary tree in order of left, root, right. To remember it, you can remember in order as left, root, right. By left, root, right, we mean we will go to the depth, and from the left depth and start from there, going to left root, then root, then right node. Okay, let's start. For in order traversal of the diagram I have given here, let's start. First go to the depth, left depth. We have 4 at the lowest, so let's first write 4. Then root is 2 of it, then 2. Then we will go to the depth. Then at depth we get 8. Then root of 8 is 5. Then we write 5. After that, in the left subtree we have no more nodes, so we will go to the root. What is root? 1. And then we will go to the right subtree in the depth most, lowest, in the left side. In the left side, the lowest node is 6, so we go to 6 and print it out. And after 6, we have no other nodes, so we go to the root, which is 3. We print out 3. Then we go to the right subtree of node 3, and in the left we get the node 9. We print it out. Then after 9 we print out 7. Then after 7 we print out 10. So the in order traversal of the tree I gave was 4, 2, 8, 5, 1, 6, 3, 9, 7 and 10. Moving on to the next traversal method, which is post order traversal. By post order traversal we mean we go to the depth of the tree at wait a second. By post order traversal, post order traversal is a depth first tree traversal method where you visit the left subtree, then the right subtree, and finally the root node. We can remember it by a trick called left right root. So let's start. According to the definition, we would first go to the left subtree. In left subtree is this. Okay, and after the left subtree we go to the right subtree and then the root. So start. Let's erase this and so let's start. Left. So by the trick I am going to do it left, right and root. Let's go to the left bottommost, which is 4, and print it out 4. And then go to the right bottommost. We don't have a child of fifth of node 5, right child of node 5, so we will directly go to the left child of node 5, which is 8, and print it out. And then as we don't have a right child, we directly go to the root of 8, which is 5. After 5, we have no other subtrees, so we go to the root of the tree we started from, which is 2, and print it out. And then go to the right subtree. We are not going to print the root this time. We will first go to the right subtree and go to the left subtree of that. The left subtree of that is 6, so let's print out 6. Then go to the left subtree again, which is 9. Then go to the right subtree of 7, which is 10. Then print out the root of that subtree 7, and then print out the root of that the other before the subtree before 7, which was 3, and then print out the final root, which is 1. So the post order traversal of the diagram I gave is 4, 8, 5, 2, 6, 9, 10, 7 and 8 and 1. And let's come to the pre-order traversal. A pre-order traversal is also a depth first search in which we first go to the right subtree, in which we first go to the root, then the left subtree, and then the right subtree. So let's and the trick for it is root, left and right. Let's first print out the root. What is the root? Not a highlighter, pen. The root is 1, so we print out 1. Then the second root comes root, left, right. After printing the root, we go to the left, and in the left subtree the root is 2. Then we print out 2. And then we again go to the left subtree of 2 and we print out the root, which is 4. And then again we go to the right subtree of 2 and print out the root, which is 5. And then we go to the left subtree of it and print out 8. and then we go to the right subtree of the original tree and print out the root, which is 3, and go to the left subtree and print out the root, which is 6, and then go to the right subtree of 3 and go to the left subtree of 7 and print right subtree of 3 and print out the root, which is 7, and again go to the left subtree of 7 and print out the root, which is 9, and go to the right subtree and print out the root, which is 10, covering out pre-order traversal. Let's erase the diagram. So I am gonna tell you a trick about all the three. For in-order traversal, you can, if you don't remember this left root right, always do for in-order traversal, make a line directly below all the nodes. All the nodes, and then start making line, a curvy line starting from here, and as the line as your curvy line merges with the line that you originally took, print it out. As in first in order traversal, which was for 4, then 2, then 8, then 5. Then after 5 it was 1, then 6, then 3, then 9, then 7, then 10. Final as is the in order traversal. Let's erase this and let's go to the trick for post order traversal. For post order traversal, you would need to make the line in the left side of the node. By left side of the node, I am showing you how to make it. See, like this. For post order traversal, I am talking about this, and this, and then as your squiggly line. No. Sorry, sir. This is I am telling for pre-order traversal. For pre-order traversal, you may need to make the line on the left side of the node, and as your curvy line touches each of the lat line, you print out the node. Let's start from 1. We in pre-order we print out 1, then 2, then 4, then 5, then 8, then 3, then 6, then 7, then 9, then 10, and then okay. And for post order traversal, you need to make the line on the right side of the node. Which side? Right side of the node. Let's make it on the right side. This, and this. And then as the square line touches each and print out the node. 4, 8, 5, 2, 6, 9, 10, 7, 3, 1. 4, 8, 5, 2, 6, 9, 10, 7, 3, 1. Okay. Let's go to the. Okay, wait a second. Thank you. Let's take the implementation of it. Let's go out. Stop the presentation. Sorry. Where is the PowerPoint? Wait a second. Sorry for the delay, people. Okay, let's stop it. Start. Okay, let's go to the implementation of a tree. So, okay, let's start. Wait a second. So I am going to show the implementation code of tree in C language. So first we will include the library, which is stdio.h and stdlib.h, and then we make the structure node. By structure node we are structure node by structure node we are going to take three variables. First is the data, that is the node, the node that contains the data. Then struct node star left and struct node star right. The left is the left child of the root and the right node is the right child of the root. And creation of the new node. For the creation of the new node, struct node star node equals to struct node malloc size of struct node. Malloc is an dynamic memory allocation system in which it allocates the size for each node, and then after this, in this to struct node and struct new node, we made the tree, and then we are trying to print out the traversal. For in order traversal, we first go to the left root and print out the data, and then right root and print out the data, and then the root, and then the pre-order and the post order similarly like this. And then here we are printing the tree. The tree structure, if we make out in our mind, is going to be like this: constructing the tree manually, 10 which has the left child as 5 and right child as 15, and 5 which has the left side as 2 and right child as 7, 15 which has the left side as 12 and right child as 20. We make the node for each of these nodes, and then print the tree, then print the in order traversal, and then print the pre-order and post order, etc. Let's run it and see the output. See, the tree is, the root node is 10, then 15, then 20. The root node is 10, and after 10, going to the left side tree, we have the root as 5, child as 2, and left side as 2, and right side as 7. Going to the right side tree, we have the root as 15, left side as 12, and right side as 20. In order traversal is going from left root right 2, 5, 7, 10, 12, 15, 20. Pre-order traversal going from root left right 10, 5, 2, 7, 15, 12, 20, and going for post order traversal we go as left right root left 2, 7, 5, 12, 20, 15, 10. So thank you everyone for joining my session. Thank you everyone for joining my session. It was a great pleasure to teaching you all. Thank you, and we will meet again soon.